Okay, 14.2. As I said at the end of the last section, this is all about arithmetic and geometric sequences. And we will be talking about those two things in depth. So our first objective is to identify arithmetic sequences. And the second, you guessed it, is to identify geometric sequences. Geometric sequences. So let's talk about what an arithmetic sequence is. I touched on the main parts of it at the end of the last lecture. So an arithmetic sequence is a sequence where each term differs from the previous term, from the previous term by some number d. We call d the common difference. So let's look at a quick example of an arithmetic sequence. So let 7, 9, 11, 13, 15, etc. be a sequence. And so we can see the common difference here. In each of these, we're going up 2, up 2, up 2, up 2. So this is, we touched on this at the end of the last section. We are adding the same number every time to get to the next one. And so we can actually figure out what our a sub n is. A sub n is going to be 7 plus 2 times n minus 1. Now, why is it n minus 1? Because this is already a 1, and this is a 2. So if I added 2 times n, 7 would go up to 11, 2 times 2. I only want to add 1, so we take away 1, or a sub n equals 2n plus 5, 7 minus 2 being 5. So this is a really nice pattern. And as it turns out, every arithmetic sequence can be thought of this way. So this is the general term of arithmetic sequences. So if a sub n is any, that's the important part here, arithmetic sequence, then a sub n equals the first term plus that common difference d times n minus 1. And this is always going to be true, which is really nice for us because it means that we don't have to think too hard about what the general term is. If it's an arithmetic sequence, we follow this pattern. So I have two problems. Now you've seen one quick example and you have the rule for you to try. So I encourage you to pause the video and try these on your own. So I'd like you to identify the general terms of A, 2, 7, 12, 17, etc., and B, the sequence with A1 equaling 3 and D equaling -5. So these are two different ways that we see arithmetic sequence problems where they ask us to find the general term, either giving us the sequence or giving us the most important parts of that arithmetic sequence. So again, please pause the video and try and identify your A sub n. I'll start going through it now. So in this one, since we don't have everything, we need to look at what the common difference is, and the common difference here is going up 5, 5, and 5. So we can identify D as equaling 5. A1 is 2. So our little formula A sub n says this is 2 plus 5 times n minus 1, or 5n, 2 plus -5 is -3. And that's our general term for that sequence. Over here, they give us the D and they give us the first term, so A sub n is 3 plus -5 times n minus 1, or A sub n is going to be -5n plus 5 plus 3 is plus 8. So in both cases, whether we have a sentence that describes information or we have the sequence itself, you have to have A1 and you have to have your common difference D. And if you don't have them, then you identify them. Once you have those, it's just a matter of plugging into our formula and simplifying. And we have our general form. So we're going to come back to arithmetic sequences again in the next section. And what we're going to do now is talk about geometric sequences. So a geometric sequence is a sequence where the ratio of any two consecutive terms is the same value. And we call that value R. And we call R the common ratio. So let's look at a little example like we did before for arithmetic sequences. So let A sub n equal sequence 12, 6, 3, 3 halves, etc. So when we look at this, our common ratio, the way that we figure it out is we take A sub n plus 1 and divide by A sub n. Or in other words, we take the second term divided by the first, and this equals 1 over 2. We take the third term divided by the second, 3 over 6 still equals 1 over 2. And then we take the fourth term divided by the third, 3 over 2 over 3 is 3 over 2 times 1/3, which is still 1/2. So this is how you check you have the right common ratio. r, in this case, is 1/2. And so now what we want to do is figure out, well, we know that each time we multiply, so the first term is just 12, so we're going to be starting with 12 for our general term, and then we're going to be multiplying by that common ratio. Once gives us a 2, twice gives us a 3, 4 times gives us a, or 3 times gives us a 4. So we don't want to multiply by too many of them. We actually want to multiply n minus 1 of our common ratios. And you can double check this. 12 if we want a 2, which is 6. That means we do 12 times 1/2 to the 2 minus 1, or 12 times 1/2. That's 6. And then a 3 should be 12 times 1/2, which is 6, times another 1/2. Well, 3 minus 1 is 2. So we can check that out and make sure that that works. And just like with our arithmetic sequences, the reason we study geometric sequences so much is because this is always true. So this would be the general term of geometric sequences. So for the sequence, not for the sequence, for any geometric sequence a sub n, the general term is a sub n without curly braces. Just to reiterate, with curly braces you're talking about the whole sequence, without it you're just talking about the term. And this is a sub 1 times r to the n minus 1, where r is the common ratio. So, unlike arithmetic sequences, geometric sequences allow us to look at more than just the first few terms to figure it out. So let's take a look at a problem together here. So we're going to determine the general term of a geometric sequence with a sub 198 equaling 32, a sub 197 equaling 8, a sub 41 equaling 4, and a sub 42 equaling 16. So if we're going to determine the general term, we need the first term and we need the common ratio. Well, the first term we need to come back to, but the common ratio has to be true for all consecutive terms. So if these all come from the same geometric sequence, that means the ratio of A198 over A197, which is 32 over 8, or 4, this has to equal A42 over A41, which is 16 over 4, which does equal 4. Okay. So that means R is 4. And so our general term, a sub n, should be a sub 1 times 4 to the n minus 1. And here's where, because geometric sequences are multiplicative and not additive, like our arithmetic sequence, we can actually use any known term to solve for a 1. So I'm going to pick a sub 41 should equal a1 times 4 to the 41 minus 1, or a sub 41, which is 4, should equal a1 times 4 to the 40th. And then all we do now is solve for a sub 1. So divide by 4 to the 40th, and we get a sub 1 equals 1 over 4 to the 39th, which is a really, really big number. It's like 3 billion or 3 trillion or something like that. So we're going to leave it just like this. Now this is kind of an extreme example because we use such a big power here, 41, 42, 197, 198. But this is the same process that we want to do. And in fact, if we do this, all we need is 2 terms of a geometric sequence, and we can figure out the general term, which then allows us to figure out any term. So let's look at another example together. So if the second term of a geometric sequence is 9 over 2, and the third term is 27 over 4, find a sub n. So this is essentially the same problem we just did, only smaller numbers. We're not looking at the 40th term or the 197th term. So we know that a sub 2 is 9 over 2, and a sub 3 is 27 over 4. And our common ratio has got to be true for all terms, so that includes the third and the second term. So this is 27 over 4 over 9 over 2, which is going to be 27 over 4 times 2 over 9. Cancel 1, 2 there, 1, 2 there, a 9 here, and a 9 here. And we end up with 3 halves. So that means our R is 3 over 2. And so our general form a sub n is a sub 1 times 3 over 2 to the n minus 1. And this has to be true for all of our terms, including a2 and a3. So a2 has got to be a1 times 3 over 2 to the 2 minus 1. a2 is 9 halves. So 9 halves has got to equal a1 times 3 over 2. So we're just going to times by 2/3, times by 2/3, cancel, 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 cancel one of those, and we get a1 equals 3. And so our final answer now, a sub n, is 3 times 3 halves times n minus 1, or to the n minus 1. And now we've found our general term. And there is one thing that we should do here, and that is once we have a1, we should check that a2 over a1 has the right common ratio, just to be sure we've done it correctly. And so that would be 3 halves over 3, or I'm sorry, 9 halves over 3, which then becomes 3 halves. And that's what we wanted. So you can think of that as just a little check. So I have a couple for you to try on your own. So find the general term. If a sub 3 equals 4, a sub 4 equals negative 12, and a sub 5 equals 36. And then B, r equals 2, a sub 2 equals 1 over 16. So two problems, two different setups. Both of these are geometric sequences. So I encourage you to pause the video and try and figure these out on your own. So first, in part A, we need to figure out our r. Negative 12 over 4 is negative 3, which is the same as 36 over negative 12. And then it's just a matter of plugging in and figuring it out. So a sub n should be a sub 1 times 3 to the n minus 1. Using a sub 3, we have 4 should equal a sub 1 times 3 squared. And so a sub 1 equals 4/9. And so a sub n then is 4/9 times 3 to the n minus 1. And here, since we already know r, we're given r, a sub n has to equal a sub 1 times 2 to the n minus 1. And we were given a sub 2, so 1 over 16 has to equal a sub 1 times 2. Divide by 2, that means a sub 1. Oh, I'll sneak it in here. A sub 1 equals 1 over 32. And so going back up this direction here, a sub n is then 1 over 32 times 2 to the n minus 1. Sneaking it in right there. So in the next section, we'll be extending sequences, the idea of sequences, into series. But for now, that is the end of 14.2.